Hello everyone, welcome to another very interesting microscopy lecture series. Today we'll be talking about phase contrast microscopy. In this talk, we will try to highlight the key important features. First of all, the working principle, okay? Then the application. What are the different applications which you can think using this method, okay? And obviously, once you have a working principle understanding and the basic physics behind it, you'll be able to apply into different sample types. But what are the advantages and as well as the disadvantages associated with this technique is what we are also going to explore at the end of the session. So stay tuned. So let's start. But first of all, we need to understand how phase contrast microscopy was invented and how it came into existence. So Fritz Zernike was the first person who came up with this concept, and he showed that by using the phase contrast microscopy, the contrast gradient in your sample can be enhanced. Now, for all microscopy images, you need to have either an enhanced contrast, which can be artificially given by the help of fluorophores, by the help of dyes, or if you are not in a way using dyes or fluorophores or external chemicals as contrast agents, you can also play with the light. Without even adding any external dyes onto your sample, you can use the technique called phase contrast gradient. So in 1934, he invented this, and later in 1953, he was given Nobel Prize for this invention. When Nobel Prize was awarded, then people appreciated the technique and it was spread globally. Sooner and later, people started working on this particular gradient technique and generated more and more contrast in their samples. And during World War II, the requirement of microscopy as unanimously was more profound, and then more and more people have started using microscopy, recognizing its potential in unraveling microbial level, cellular level structures, and also going on to the physiology behind it. During World War II, when the microscopy demand increased, then the company founded by Mr. Carl Zeiss, he actually started taking this concept of phase contrast gradient technique and started manufacturing at the company level or at the industrial level. And at that time, the phase contrast gradient technique started coming as more or less like a basic feature in the microscope, where the objective was modified, and in the market, phase contrast gradient enabled my objectives, or today as we know, phase objectives. Thus, the phase objectives was highly commercialized, and as we can see, it has become a very integral part of today's microscopy configuration. Now, let's understand the working principle behind the phase contrast and how this contrast is being generated in your samples. So as you can see here, this is the basic microscope structure, and it's an upright microscope configuration I have tried to portray here. And in this upright configuration, where we have multiple objectives loaded onto the nose piece, but we also have, if I can show you here with the help of my pointer. So these are the objectives, okay? As you can see, the number 1 is the objective part here. This is basically the stage. On top of the stage, your holders will be there, or accessories will be there, which will enable holding of different types of sample holders, be it glass slides, be it Petri plates. And this particular attachment will enable your sample holder to be fitting onto the stage and fix it properly. As we move down, so number 2 is the specimen, number 3 is the stage. And if you can see here, this is not only the stage, but also you can see a small portion coming here. This is the annular ring and the condenser lens. So in the annular ring and the condenser lens, together, you can see it is positioned just below the stage, And here you have the light source, which is nowadays either integrated at the back side of the microscope frame, which light is transmitted here, and they will have a mirror. Through the mirror, the light is reflected, and it is a transmitted mode of illumination where the light comes from one side of the sample and the collection of the image is being captured from the other side of the sample. So it is light has to transmit through the sample and move to the detector or the camera, whatever, or to the eyepiece. Now, what phase contrast attachments, if you put in your microscope, you will have the effect of contrast using this methodology. To understand that, we need to have basically two things. The first and the foremost is, if you see here, the objectives are phase compatible objectives, means these are not normal objectives. These objectives, when you actually order your objectives, initially you have to tell that I want a phase objectives, and this phase objectives, the speciality is you have a phase plate, as you can see inside this objective. So this phase plate is an integral part of the objective, and it is an additional thing, attachment inside the design of the objective. That is why phase objectives has to be taken if you want to do this phase gradient contrast. The next most important thing is, when you have the condenser lens and everything, you need to also have a phase ring. So once you have the phase plate, the other in the condenser, you need to have a phase ring. Now this phase rings can be of different sizes depending on the objectives you are using it, and all the objectives you are using, like suppose you are using a 5x objective or you are using a 20x objective, it is irrelevant. The point is, whatever objectives you are using it, that objective has to have that phase plate inside it, and that phase objective you have to use it in your microscope. In addition, you need to have the condenser, which will help you to create that phase shift effect and give you eventually a contrast generation where your background and foreground intensities are slightly different. In this design, if you see here, this is where the illumination was, as we were showing in the previous one. This is a little bit complex microscope, as I'm showing here. This is the illumination module or the housing where the light source or the lamp is based, and the light comes from the bottom. It goes straight up, if you can follow this marker. And at the bottom of the stage, if you see, this is the first one where you have the annulus, and this is in the condenser. So it is commonly known as condenser annulus. And in this condenser, if you see the design, it's basically ring, but you have concentric rings. And how it is designed is this annulus condenser and the phase plate within your objective, they will be looking like concentric rings. One will be a little larger in the diameter, one will be a little less in the diameter. And by putting this annulus rings in the light path, what happens is we are actually trying to see the phase shift happening because of the light interacting separately with your background and separately with your foreground, and foreground is your sample. So you want to have, so how a contrast is generated? If I'm not adding an additional dye which will give me a color, if I have to generate as natural sample a contrast, then I have to do something in my light path where either the light passing or there is a change in the behavior of the light passing through the sample as well as the background. And if this change of behavior can be captured, either it is collected or it is somehow because of this change in behavior, the light is either suppressed or allowed. So we can have varying intensity in the background as well as the foreground. And if we manage to successfully vary the intensity of the background and the foreground, I think the contrast generation can be done. And that is where the role of annular ring as well as the phase plate comes into picture. So if if these two components are positioned, one in the condenser, one in the objective, then we can capture the phase contrast gradient, as I mentioned earlier. Now let's see the light path. So this is the light source, and from the light source, you see this is basically the collector lens, and after the collector lens there is an aperture, whether how much light you have to open or close, and let's see how much light has to go to the sample or fall onto the sample. That can be regulated. As we move ahead, then there is another aperture, and then comes your condenser annulus. So your condenser annulus, if you see, it is basically a small ring inside where the light will only be passing through. There is blocks here. If you see, light is blocked here in all the black portions, and it will only be allowed to pass through the small slits or small ring where an opening is there and light will pass through it. Next, you have your condenser ring, then your stage on which your sample has been positioned, your objective, and inside the objective comes again the phase plate. Now, if you see the phase plate, in contrast to the annulus, if you see in annulus, these are the only two openings where the light was forced to pass through it. There was a lot of blocks, but light has to pass through the small ring opening which was there in the annulus. On the other side, if you see in the phase plate, light is allowed to pass, but it is only blocking these portions. So the ring which you saw earlier in the annulus, which was allowing light to pass here, in the phase plate, it is just opposite. That ring will be stopping the light, and rest the light can pass through rest of the area. So basically, if you see here, there is also a small opening and blocks, and light is forced to pass through it, and because of which there is a phase shift being happening and it is being captured. So the diffracted light you see here, it is allowed to go to the imaging plate. Now that's interesting. You might ask me, okay, if I am putting an annulus and I'm putting an objective, the sizes of the objectives, or basically the magnification and the sizes of the annulus rings, will it vary? Yes, it will vary. And it will vary with respect to what? It will vary with respect to, first of all, your magnification you're using it, because based on the magnification, how much light it will be collected. So there it will be dependent, and consecutively or in correspondence to what magnification objective you are using, you need to use the annulus respectively. So there are a lot of annulus are there. So we say phase 1, phase 2, phase 3, and as you can see here, for 4x, so this is for 4x, this is for phase 1 is for 10x, for 20x also phase 1 can be used, and phase 2 is mainly for 40x or higher magnifications. And as you can see here, the diameter of these rings keeps on varying, or basically if you notice it, the inner circle, which is this one, the diameter of this circle keeps on reducing, and it is becoming a much more smaller circle as we increase on to our magnification. And correspondingly, if you see here, the opening is also gradually. So what happens is, when you're using a lower objective, the amount of light passed through it will be more. As and when we increase your magnification, the light collection or the light allowed to pass through this annulus becomes less. So you have to keep a note of it. Now, there are, as I said, there are multiple annulus will be there. So in the condenser, there will be a plate on which, based on the objectives, there will be multiple annulus will be there. As and when in the nose piece you change your objectives, suppose I'm working on 10x, I will use a phase 1 annulus in the condenser. If you have a motorized condenser, then it will be automatically aligned because it will be pre-calibrated. But if you have a manual one, you have to make sure that your objective and corresponding annulus has to be there in the light path, then only you'll get the proper phase effect. Now, if you see this image here, this is a slider, or this is where you have three positions are there and different annulus sizes are there. The last one being a blank. So in that you can change the position. If you are looking for a simple bright field image, you have to remove the annulus and you can capture a bright field image. Now, if I take a bright field image, my image is going to look like this. And in this, the structure wise, there it is visible. Yes, I agree to that. But if you see, the contrast generation or enhancement is not there from the background and the foreground. Whereas in case of a phase image, if you see here, the background and foreground, you have a clear cut demarcation, and you can identify these are the boundary of my sample. So why phase contrast has become popular? Because first of all, you are not adding any extra chemical onto your sample. Sometimes your samples might not be liking it. So if you're doing some live cell experiments, adding an extra dye, first of all, will take time because you need to buy a consumable for that. Second, it's price worthy, so you have to have spend your money onto buying some fluorophores or dyes. And if you're doing bright field, then also you can do it. But again, when you are doing it in live conditions, suppose your cell line is there or your cells are there, they are happy, healthy, the moment you add your dye, they are not liking it. So what will happen? The basic morphology functionality will change. Unlike if I can use the light and then generate a contrast, so they are in their native state, I'm not adding any external dye, and they are not irritated. And by using this phase contrast method, I can generate the contrast and make my background and foreground separate. Now your morphology is much more prominent, your cells are healthy and happy, and you can also capture them in live cell processes. Means if I give a proper live cell environment, I have my CO2, my temperature, my humidity, everything under control, then I can monitor them. Simple budding of a yeast, simple cell divisions, right? For that you don't have to add any of the dyes, you just have to put your phase objectives, put the proper annulus in the condenser, and you will be able to see them in live state, and your morphology will be picture perfect, right? And that is an additional advantage where you want to know whether your basic cells are happy or not, whether your sample is healthy or not. And morphology is very crucial when you have to show multiple images, especially in live cell setup. This is another example where you can see multiple examples are I have tried to see. And if you can notice, there is a outline which has become sharper. Your background and foreground, where is your sample, where it has been focused, you can distinguish them very easily. And it will also help you to track, like if I do a simple cell counting, if I do simple experiments where I don't have much complications, I just want to see before passaging how many cells are growing, what is the rate of their growth, I can do such simple things. Just put the sample in the microscope and start recording it, start time-lapse experiment, and you'll be able to see how fast they are growing, what is the morphology, how connections from one cell to another cell, how fast they're making connections without adding anything. It's that simple, right? So point is, you have to first identify on what type of samples your phase contrast has to work, right? And whether your magnification is suitable for the size of the sample you are taking. For example, if I'm using a cell line, right, I have a mono layer and I can easily use 40x objective. But on the other side, if I'm working on bacteria, I'm working on microorganisms, where even your forget about 5, 10, 20x, even your 40x at times might not be enough to give you that resolution. So your contrast generation will not be enough, right? How we can do that, I'll come in a while at the end of it, where we will be also introducing some other techniques in addition to this. Thus, let's explore about the advantages as well as the disadvantages. So in advantages, as I said, you can do live cell imaging without adding any dyes, no stainings required. You simply have to put your samples. If you have a like fast growing, slow growing, dynamics, movement, morphology, cell division, you can study them without giving a second thought. Second, you can generate better contrast compared to wide field, where your background and foreground will be much more separated. So small structures will be much more clear and crisp, and ideal for studying and interpretation of thin samples. Why? Because if you have thin samples, the contrast generation is better in this case, and the morphology will be much more profound. But That is not all. There are also disadvantages associated with it. So I mentioned two things. First, you don't have to add staining, and these are all advantage part. You need to use thin samples. Why not thick samples? If I have thick samples, the edges will always be a problem. So in phase contrast, the biggest disadvantage is a halo effect, right? A halo effect, I'm a god, and if you see a light of a ring, or basically an illumination ring behind my head, and that is we say as halo, the similar effect will be seeing it in your samples, and that is not at all required, or that is not wanted, because that will somehow, if you have two structures very close to each other, the halo of one might be falling onto the other sample or the other cell nearby, and then the sharpness will be compromised. So halo effect is the problem, and as the thickness of the sample increases, this halo effect increases more. So the sample thin, the better, and you will have little bit or less halo effect in your samples. You also have annuli or rings limiting the aperture to some extent. So the light collection, as I said, in lower magnifications, you have more light passing through it. As and when you increase your magnification, the light collection becomes less, which in other way, is also a problematic, because as and when you increase your magnification, the collection of light inherently becomes very less. So that is another disadvantage with this technique. Already I mentioned, with the thick samples or thick organisms, volume samples, tissues, organoids, spheroids, it is a complete no, because you'll have a too high halo effect, your edges will not be sharp, and then that will give you a very blurry image, right? It will not be sharp, and all the images will always appear to be grayish to greenish. Okay, so that is something, another problem, because of the phase shift, we always will capture images more or less in gray to grayish color. Okay, for your ready references, you can always refer to these papers and publications, and they will be giving you much in-depth understanding about this technique. So you can always go and read out more and more. If you have any questions or any queries, please feel free to reach out to me. Okay, so understood the concept, liked it? If you liked it, great, give me a thumbs up. You can share your comments, you can reach out to me. Please feel free to ask questions. I have more informative videos coming very soon.